An arc flashes across the terminals of an industrial substation. The factory lights dim for a moment. The breakers trip, and the heavy metal switchgear stands intact. A routine electrical fault, cleared safely. Now we rewind. The exact same facility, the exact same voltage, and the exact same short circuit. But this time, the fault starts a few milliseconds earlier. The resulting surge instantly vaporizes the metal contacts and blows the switchgear apart. The difference between the routine trip and the catastrophic explosion had nothing to do with the physical location or the size of the power source. The deciding factor was the exact millisecond the fault made contact with the grid. To understand how a microscopic sliver of time multiplies physical destruction, we have to look closely at the internal anatomy of an alternating current waveform. Electrical engineers cannot design protective equipment to handle an average fault. They have to run the math to anticipate the unluckiest possible fractions of a second. Under normal conditions, alternating current flows in a predictable rhythm. The voltage and current waves constantly oscillate back and forth, perfectly balanced above and below a center zero axis. When a short circuit happens exactly at the moment the voltage wave is at its highest peak, the result is what engineers call a symmetrical fault. The amount of current surges to massive levels, but the wave itself remains vertically centered and predictable. But the electrical grid is packed with transformers and motors that create inductance. This physical property, measured as the system's X/R ratio, acts like a massive magnetic flywheel, violently resisting instantaneous changes to current flow. The absolute worst timing for a fault is the exact millisecond the voltage drops to zero. Engineers call this a 0-degree closing angle. At zero voltage, the grid's inductance forces a mathematical correction. Because the physical coils and transformers block the fault current from jumping instantly, the system introduces a decaying surge of one-directional energy, known as an aperiodic, or DC, component. This direct current offset physically pushes the entire alternating sine wave upwards. Instead of oscillating evenly around the center, the massive surge of fault current is lifted completely off its baseline. This distorted off-center wave is an asymmetrical fault. By shifting the wave upward, the grid's magnetic resistance stacks the current on top of the DC offset, creating a massive, localized peak. The immediate danger hides in the first cycle of that shifted wave. The highest crest, the peak short-circuit current, reaches an impossible amplitude. Physical force scales with the square of the current. That artificially high peak acts as a mechanical bomb. The resulting magnetic fields exert thousands of pounds of shear force, instantly bending steel enclosures and ripping solid copper busbars off their physical mounts. If the equipment survives that initial concussive blow, a secondary threat takes over. As the asymmetrical wave pulses and decays over the next few cycles, it pumps extreme sustained heat into the surrounding hardware. This chart maps the M factor, plotting the time-dependent heat effect of the decaying DC offset. Engineers use this decay curve to calculate the Joule integral, a measure of total thermal energy, dictating exactly when copper wires melt and insulation ignites. An asymmetrical fault delivers a precise 1-2 punch. First, an instantaneous mechanical shockwave on the opening cycle, followed by rapid thermal melting if the circuit is not immediately broken. The inception angle of a short circuit is entirely random. Whether a tree branch falls across a transmission line or a worker drops a metal wrench across a live busbar, no one controls the exact millisecond the connection is made. Because the timing is a literal lottery, the power grid and its protective switchgear must be preemptively armored to survive the absolute worst-case scenario. Heavy-duty circuit breakers undergo rigorous testing to earn specific interrupting ratings. These ratings prove they can physically separate their contacts and extinguish an electrical arc even under the extreme stress of severe DC offsets. For even faster protection, engineers deploy current-limiting fuses. These devices are designed to react in less than a quarter of a single alternating cycle. They physically melt and break the circuit so fast that the devastating peak short-circuit current never even has the time to fully form. To coordinate all of this, electrical engineers run meticulous short-circuit studies. They calibrate protective relays to guarantee that breakers trip fast enough to prevent the thermal buildup that causes lethal arc flash explosions. The modern electrical grid operates as a tightly coordinated defense network. It is mathematically armored against the raw power of millions of watts and against the unluckiest fractions of a second.